Okay, so now we start our study of exponential growth and exponential functions, and then we transition to logarithmic functions. So for this one, this example, they're telling me a couple things. They're telling me that if tuition is currently 1,050, I'm guessing per credit. They don't tell us this. And they're telling us that it's increasing by 7% per year. So this is an annual growth rate because they're telling us per year, versus that's different than a continuous growth rate. If you look in the book at those examples, continuous growth rate, and we're gonna look at some continuous growth models here in a minute here. But because this is an annual, and actually I should give you the general forms for this. So this is y equals, or f of x equals, some initial value times some base to some, either, in this case it'll be years. I'll use x because I'm using x and y, but you could use t for years. And if it's a continuous model, it'll look something like this. It'll y equals to a, where a is still the initial value, but then use e raised to some continuous growth rate times x or t. Okay. E is a number. There's a lot of videos about what E is. If E is a number, there's going to be between 2 and 3, and that actually works out to be 2.7. No, what is it? 7.1. I don't know. We'd have to go look it up in a calculator or a number. It's closer to 3 than it is to 2. It's natural base. A lot of things in nature grow continuously rather than annual. And we'll look at that in a minute here. So the other thing I should add on about the annual model is that base can be found by taking, well, it can be taken as, I tell my 8th graders when I talk about exponential growth, we talk about it's 100% plus the growth rate, or the growth percent, and divide it by 100. But you guys are a little more sophisticated than that. So we'll just call it about 1 plus r, where r is a growth rate. Now, if it just so happens, if it's a decay, if it's decreasing, it'll be 1 minus the rate. Or you could think about it as the rate. If it's decay or decreasing, the rate's negatives, okay? And then, of course, a is the initial value for all of these kind of problems in this section. So I'm going to write y equals 1,050 times, well, I'll write 1 plus 0.07. Remember 7% is 0.07 is a decimal, 2 decimal places to the left. I say that, you can tell people have gotten that wrong before, so I don't want you to. So I could also just jump to 1050 times 1.07 to the x power. And that's the model. And then they're asking me to make a prediction in 5 years, so that's just writing the x is 5. And you're going to raise that to so what I would do in my calculator, and of course I don't have a calculator on this device, I would do 1.07 to the 5th power, so 1.07 raised to the 5th power. I got what did I get? 1,050 times 1.40. 1.40255, yada, yada, yada. So I'm just going to go, I've got that number in my calculator. I'm just going to go times 1050. So that means if it continues to grow at this rate, tuition would be 14.72. They want the nearest dollar. I would round to that. Okay, so that's how you deal with it for the annual growth rates. So I don't see an E in this equation, so I'm going to assume that this is an annual model, not a continuous model. So I see the initial value, the y-intercept in this case, is 1,000. And then this is a decay model. The reason I know it's a decay model is because that's less than 1. If that was more than 1, it would be a growth. And I know this is a decay because it's less than 1. So how do I find that rate? Well, I know 1 minus the rate, because it's the decay model, has to equal 0.83. So if I subtract 1 and then I divide by the negative, don't I get 0.17? So a 17% decay rate. And do I need to do anything else? And that's number of years, T. Let's see, was there something else I was just going to talk to you about before I left this? There's something that came to my mind I wanted to do. I don't remember. All right. Well, I know it's a decay. I know it's less than 1. Something along those lines. Usually the bases are positive. We don't usually have negative bases. It could be, but there's some weird things happen when you have a negative base. Even odd powers. So we don't usually go there with those. So they're telling me a couple things with this. They're telling me I've got these 2 points. For now, they're telling me use y equals ab to the x. Well, they're telling me that, but that's the easiest way to go. Remember how a is the initial value or the y-intercept, and see how that's a y-intercept because x is 0, y is 3? We can do this. We can say y equals 3 times b to the x. And that checks because when I substitute in 0 for x, anything to the 0 power is 1, so I get 3. So now we got to find the base. And I have this other xy, so can't I say 18 equals 3 times b to the 3rd power? No, this 3 is that 3, right? So I'm going to divide 18 by 3, I'll get 6. So b to the 3rd. And then to solve that power equation, I'm just going to take the cube root of both sides of this equation. And I could leave it as cube root 6, but often we're just going to actually find out what the cube root of 6 is and do some rounding. 6 raised to the cube root. Did you do this? I'm working with an older style calculator here. I could find the button that does cube root 6. I can also do 6 raised to the 1/3. Remember going back and forth. My on-the-ground pre-calc class at Oxbow, I always do a little bit of this exponent review because they're always a little rusty with it. And if you're an Oxbow student watching this, you'll see, oh yeah, he did do that. But cube root, remember, you can take, if I have well, let's call it the nth root of a to the b power. I can write that as a raised to the b over n, where the n's the index. So this is, and I won't usually hunt for a button that'll take roots. I'll write them as a fraction and deal with it this way. And that's exactly what I'm typing in this calculator is 6 raised to the 1/3. I think I'm doing that. Let me see. And it's important to use parentheses unless you have a newer model calculator that treats it like an exponent. This one doesn't. So that tells me b equals 1.81. I'm going to go 4 decimal places. Usually that's enough for my open math, and it's certainly enough for me. So that's the base. So y equals 3 times 1.8171 to the x. And that's all this question's asking us. What if I wanted to ask you, what's the growth rate? How much is this equation grown by? I know it's a growth because this is over 1. And so if I think about 1 plus r being b, well, doesn't r have to be 81 or 0.817 or 81.71%? So that's what that's growing by. It's a good, healthy growth rate. So what's different about this one is I don't have a y-intercept. So I'm going to initially set this up. I'm going to say y equals, I know it's what, yeah, all right, y equals ab to the x. So I'm going to substitute in x and y. So 5 equals, I don't know what a is, I don't know what b is, but I know x is 2. And for this other one, I know y is 1 equals a times b to the 4th. And then what you can do is do some substitution. We have 2 equations with 2 unknowns, so we go to systems of equations. They aren't linear, but we can substitute. So I'm going to divide both sides of this equation by b squared, and that's what a is. And then I can come back over here into this equation and replace a with 5 over b squared times b to the fourth. And then remember, when this is b squared divided by b to the second, b to the fourth divided by b to the second, so we can subtract the exponents. So that becomes 1 equals 5 times b to the second, which is nice. We'll divide by 5, get 0.2, 1/5. And then I'll take the square root of both sides. And what's the square root of 0.2? I'm getting 0.4472. So b equals 0.4472. And then I got to find the initial value, right? I need to find a. And I see that 5 divided by b squared is a, and I know that b squared is 0.2 or 1/5, right? So why can't I just do this? 5 over 1/5 equals a, and isn't 5 divided by 1/5 the same as 5 times 5 over 1? So a equals 25. So this equation will be y equals 25 times, and I'm going to do the 0.4472, the 72, to the x power. And that should work for this equation. It should work in my open math, and I'm sure it works in the book. Now we're getting into where do you use this stuff in real life. My wife and I were just had a phone conversation with our Dow Jones financial advisor, who we talk to him about once every couple of years because we don't change two things too much. So compounding interest is what it's all about. If you're in your 20s and you start having some free money, start doing that regular savings. You'll thank yourself in 40 years. And if you're not in your 20s and it's starting to creep up, you might want to start thinking about investing. You got to get that emergency fund saved up first, in case something happens. But and I know school's tough. Having kids and all that's tough. It'll start a little bit though. I didn't know this was going to be a personal finance lesson, did you? I start with $1,000, and it's a savings account that earns 1% compounded monthly. And when the one is to find the amount in 10 years. So what you need is this. You need y equals the principal. Or actually, let's do this. Let's pull it into real life. Instead of y, let's call b the balance equals the initial principal times 1 plus the interest rate as a decimal. And you can find all these all these spelled out in the textbook. Divided by the number of times they figure the interest each year. That's the number of compounds raised to the number of compounds each year times the number of years, and I'll call that t. So all we've got to do is substitute all this in now. So I know I start with $1,000 times 1 plus 0.01. I got to take the interest rate and make it a decimal, or the APR and make it a rate, right? And then divided by compounded monthly is 12, I'm sorry. And 12 times a year for 10 years, they're going to pay us interest 120 times, sorry. And you can key this in your calculator right off. You can work, depending on your calculator. If you're running off your phone, you probably will have to work backwards. Let's see, I'm going to find that. I'm going to do 1 plus 0.01 divided by 12. And I'm getting 1.00833, then a whole bunch of threes. There it wouldn't work to round to 3 decimal places because that would be 1. So you'd have to make sure to carry enough. I would honestly carry that on my calculator. Now, if you've got a graphing calculator, or if you're using Google Calculator, you can key this in just like this. I might write 120 instead of 12, but you can key instead of 12 times 10. But you can key that in right the same way. If you're using your phone, I would calculate. Here, let me get a pointer going. On your phone, calculate this, hit the y to the x key or x to the y key, and raise it to the 120 power, then times it by 1,000. Because I've got a scientific calculator, graphic calculator here, I'm just going to take this, since I already got this in my calculator, raise that to the 120, and then times that by 1,000. Let's see. Times that by 1,000. So that in 10 years, putting into a savings account that's only earning 1% interest, you'll have only earned $105 in interest. Because the new balance is 1,105. Okay, kind of sad, but you don't lose it. It's there. It's always there when you need it. We can do some discussion in the discussion forums, I guess, to go beyond this. I'll keep this video short. So now, what's different about this equation or this problem? See where it says compounding continuously? So this is not an annual rate. This is a continuous rate. So now we're going to be using, that y equals a e to the kt formula. And so we'll start with $1,000, e raised to the 0.01 times 10. And you'll see that the number of compounds will have a slight effect on it. So what I'm going to clean this up just a minute. 1,000 e raised to the 0.1. And that's what I'm going to do right on my calculator. I've got an e button, so I'm going to do 1,000 second e to the x 0.1. And that continuous growth rate doesn't pick up much more, but it does a little bit. What did I have with the... Yeah, I picked up an extra 5 cents. If you can find an account that pays the interest more often, go for it. But the interest rate always does better than the number of compounds. So always go for the higher interest rate if you can. Okay, so that's continuous rate. And continuous is the buzzword you want to look for. Careful reading, close reading here will pay off for you. All right, so here's another notice continuous, and it's hourly, and I start with 1,000. So y equals the population equals 1,000 times, don't want to use a parenthesis, I want to use e raised to the 0.04 to the t power. Since they're telling us it's a day, isn't that 24 hours? So we just got to key that right in. I'm going to do 1,000, since my calculator will do it. 1,000 e to the 0.04 times 24. So that works out the bacterial will be up to 2,100 and 2,600. Well, my calculator, this would be a good time to talk about this too. My calculators give me this kind of answer. And since I can't have partial, and I mean, I guess I could round up, but typically we won't. So we would leave it at 2611. So that 1,000 bacteria would grow to that rate in one day. Okay. We'll do this again in section 3 a little bit differently, but this works pretty well. I know that y equals AE to the 0.04 t, where t is measured in hours. Now, if I want to go to an annual rate, an hourly rate in this case, those look like this. Y equals AB to the t, or AB to the x. And the only thing that's different here, doesn't the e to the 0.04 have to be the same as the t? Do you see how we've got an a and how we've got an a and how we've got a t and got a t? If I come back to this equation and slap parentheses around this, do you see how that's the same as the b? And our calculator will do this, so all we have to do is raise e to the 0.04 power. and I'm getting 1.0408 with some other decimals. And remember, B equals 1 plus the rate, so doesn't the rate have to equal 0.0408 or 4.08%? And that's my hourly percent growth. Okay, so hopefully that helps. Hopefully this gives you enough practice to get either do the textbook work. I encourage you to do some of those textbook problems. It won't take you long. It'll make the math go faster. Okay, I'll stop this video and get it uploaded.